Hello, abstract algebra students. Today is our fourth lecture in abstract algebra in chapter 1, and today we are going to look at semigroups of matrices. Normally this lecture is on the Tuesday of the second week of the semester. We have already looked at the familiar semigroups, all 12 familiar sets under multiplication, and 9 of the familiar sets under addition. We have also looked at R under double multiplication in the last lecture as a semigroup. And now we're going to branch out into the world of less familiar sets. However, we're going to bring back some matrix algebra to life, and we are going to look at semigroups of matrices. So remember, as we discuss a semigroup, the first thing that we need to do is come up with an algebraic structure to examine. And an algebraic structure is three things. It is a set, a definition of equality, and an operation. So we'll start by discussing the set, the equality, and the operation that we're going to be looking at today. The set is going to be something called M2R. Now, what M2R is an abbreviation for is matrices 2 by 2 with real entries. So M2R, if we define this, is going to be the set of all matrices of the form ABCD such that ABCD are all members of the set of real numbers. So this is the set of 2 by 2 matrices, entries all in real numbers. Now, we need a notion of when 2 by 2 matrices are equal. So if we take two arbitrary 2 by 2 matrices, say A, B, C, D, and E, F, G, H, these are equal if and only if every pair of corresponding entries are equal. So the top left entries have to be equal, A equals Z. The top right entries have to be equal, B equals F. The bottom left entries have to be equal, so C equals G. And the bottom right entries have to be equal, D equals H. So what this says is two matrices are equal when they're 2 by 2 matrices. They're equal if and only if all four pairs of corresponding entries are equal. Now, there are two operations that we're going to look at. One that is very intuitive and one that is very not intuitive. Either of these operations will make an algebraic structure. And the two operations that we're going to look at are matrix addition we define this as follows. We have a couple of 2 by 2 matrices. A, B, C, D plus . E, F, G, H. And the way that we add matrices is we simply add the corresponding entries. So we're going to get here A plus E, B plus F, C plus G, and D plus H. This is the intuitive. This is the intuitive operation. How do you add matrices? Well, you just add the entries. Now, the less intuitive operation is matrix multiplication, because it turns out when you multiply matrices, you don't just multiply the two entries. Now, there's a formula for matrix multiplication, but I would not recommend trying to memorize the formula, because there's an easier way to actually understand what you're doing here. Let's say you have the matrix ABCD, and you want to matrix multiply it with the matrix EFGH. Now, you're going to get a 2 by 2 matrix. Here's how I figure out what this matrix is. The first column of this 2 by 2 matrix is going to be what I get if I take ABCD, the matrix, and multiply it with the matrix vector product EG. So go back to Math 130, matrix algebra. Do the matrix ABCD times the vector EG. This thing from the first day of matrix algebra. You get AE plus BG in the first entry. In the second entry, you get CE plus DG. Now, that's how you get the first column. You take the matrix on the left times the first column of the matrix on the right, gets you the first column of the product. Now, if I want to get the second column of the product, I just take the matrix on the left times the second column of the matrix on the right. So now view this as the vector FH. I get AF plus BH. I get CF plus DH. Okay, so again, I do not recommend trying to memorize this matrix. I instead recommend trying to understand the first column of the product is the matrix on the left times the vector that is the first column of the matrix on the right. And the second column of the product is the matrix on the left times the vector that is the second column of the matrix on the right. If you remember this column-wise, it will be a lot easier than trying to memorize this formula here. Okay, often it helps the first few of these that students do cover up the entries on the right and just do the first column. Then cover up the entries on the left and just work out the second column. Really, the matrix times matrix product is just every column of it is a different matrix times vector product from matrix algebra. Okay, so now we have a set, we have a notion of equality, and we have two different operations. So we want to see which of the semigroup properties hold, the abelian semigroup properties hold, commutative, associative, well-defined, and closure for each of the two operations with the set M2R. Matrix addition is the easier of the two operations, and all four properties hold there. I am going to let you work that out on the homework. In the rest of this lecture, I am going to examine matrix multiplication. I will first prove that matrix multiplication is not commutative, but then I will prove that it is associative, that it is well defined, and that M2R is closed under matrix multiplication. And that will be what we do today.